Chemistry 1411 Exam 1. I'm going to just run through some slides from a previous face-to-face class. Perchance it prove useful and just give you my thoughts as I come across it. Chapter 1, what you need to know definitely is the definition for chemistry. You're taking chemistry class, you should know what that is. And we talked about the scientific process. One key thing to know, and this will become important later, is chemistry builds in the macroscopic, the microscopic, and it uses symbolic language. H2O is symbolic language. That's water. Macroscopic. We live in the macroscopic world. We can see 12 grams of carbon. We live in the macroscopic, but the nanoscopic, we can't see 12 atoms, but Mother Nature can. And so a lot of the calculations will be trying to do calculations here for things that are happening here. Okay, so let's see, 3 phases of matter, easy enough. Solid, liquid, gas. Atoms and molecules, a little bit of tricky. Just make sure you know, and you should, the difference between a molecule and a compound. They're similar but different. 4 classes of matter, what are they? Elements. Elements go together to make compounds, and you can mix compounds to make what? Mixtures. Key questions normally come through: how do we differentiate these two, pure substances to mixtures? And that's based, you can separate those based on physical means. And elements and compounds, you can only differentiate those chemically. Okay, moving right along. Intensive and extensive properties, chemical and physical properties. Standard fare on an exam is to give you some of these. Is it chemical and physical, or is it extensive, or is it intensive or extensive? So kind of know those. There's the type of questions you get right there. Which are these? Chemical, physical, or only? And again, this is a brief view to just show you what I'm thinking. There's not near enough time to, in this video, work sample problems and explain a month's worth of material in 20 or so minutes. Periodic chart, make sure you're familiar with all the bits and pieces and that. Measurements. Okay, a measurement is a number plus a unit. So where that all comes from is some things deal with measurements, some deal with numbers, some deal with units. For example, units, what are we talking about? Well, typically we're talking about something that is SI unit or metric unit. So that was all explained. But just so you know, the 7 big metric base units are those 7 right there. They're called the SI units. Everything else is built off of them. Continuing on. Okay, so you are responsible for memorizing 7 particular prefixes. Those will not be given you on an exam, and there they are. Density, your first formula. It is a physical property. Density, mass divided by volume. Very easy. Plug and chug. You can use that formula. You can do it algebraically, or you can, what I normally do is use the unit and use dimensional analysis. No difference between accuracy and precision. In short, accuracy is the ability to hit the bullseye. Precision is the ability to have a tight grouping. They tell you different things. Determining uncertainty. We're on the measurements, but how do you know how good a number is, if you will? Well, that's this horrible thing called sig figs. Yes, you have to report how many significant figures a number is good to. I can tell you there's 1,000 people in the stadium, but do I mean there's exactly 1,000? Exactly? Or do I mean, it's pretty near 1,000? Well, what I mean is it's about 1,000. But if I wrote the number this way with a decimal point there, that would mean there's exactly 1,000. That's the power of this thing called significant figures. I can look at a number, anyone writes, anywhere in the world, and I can basically tell how good that measurement was. Okay, so what you need to do is there's 3 types of measurement uncertainties you're going to need to know about. The simplest one is for a single number. Give you a number, how many sig figs? An operation, that is where you multiply, divide, or add, subtract. There's videos on that. And then a mixed operation, which is basically where you have at least 1 multiply, divide, and you have at least 1 addition, subtraction. There are some examples of each of those. Sig figs, to do a single number, I would just use the box and dot method. That was taught on a couple of videos. There is actually the development of the box and dot method, and you'll know that was actually developed at Angelina College. For what that's worth, significant figures in an operation. Here's a couple of examples of that. The key thing I would give you here is you need to know two things. What I call sig figs and what I call places. Okay, sig figs. When you multiply or divide, you pay attention to the number of sig figs. But when you add or subtract, you pay attention to places. The book typically only talks about sig figs. I like to break them out into two things because they're very different. So you only have 4 operations: multiply, divide, add, subtract, at least in this class. If you multiply, divide, you are going to count sig figs and you're going to forget about places. If you add or subtract, you're going to count places and forget about sig figs. So I hope that helps you as you try to get these worked out. Let's see. If you have a mixed operation, trust me on this, do yourself a favor. The first thing you're going to do is just all of the addition subtraction, which in this case was that. Then you rewrite it, and then the next step, you do the multiplication division. Why do you do these in separate steps? Because you use different rules. You're going to use one set of rules for the second step, and you're going to use one set of rules for the first step. Do not try to do a mixed operation in one single step. You have been warned. Okay, and this is to kind of help you. I normally think about a mixed operation as being boxes, where the first box I do the plus minus, and the second box, and this reminds me to do it in discrete steps. Exact numbers, you can ignore those when you're counting. They have an infinite number of sig figs, which means you can just ignore them, because what you look for is the thing with the least number of sig figs. That's what's limiting in your answer, not the one with the most. So there's a list in your videos and in your text and posted on the blackboard. The things that comprise, or most of them, what we call exact numbers. Right, there's some examples here of what you do. For example, if you multiplied the number 100 by 2, or you added the number 2 to it. By the way, the trick with all of this is to know the number 100. That number is very different from a 100 with a dot after it in the world of science. Okay, there's a couple of more examples. Okay, 2 ways to work things now. You can do things algebraically, and there's an example of a density problem worked algebraically. Algebraically means you plug the numbers in, into the formula, and you rearrange and calculate the one that ain't got no number. In this case, you were given density and you were given mass and you were not given volume. So you rearrange those and you plug it in. These are basically plug and chug type. The second way to work it is for dimensional analysis, where you pay attention to the unit that you need. And here's an example, and this is also in the video, of how to use dimensional analysis. The key thing is, algebraically, you are working from a formula. Dimensional analysis, you are working from the units. Very different approach. See, a Ford Mustang has a 5-liter engine. What is the size in inches cubed? I want to know inches cubed, so I put it here. I'm only paying attention to the unit. And I'm going to start with 5 liters because that's what it starts me. And I'm going to work through the dimensional analysis process until what? Until the number I'm looking for shows up as the only unit left on the right side. That's how I know that. Okay, so there's a lot of questions doing that. Temperature, you need to do temperature conversions. These 2 temperature conversions, they will be given you on your cheat sheet. So there are 6 possible things, conversions you need here. Kelvin to Fahrenheit, Fahrenheit to Kelvin, Kelvin to centigrade, centigrade to Kelvin, centigrade to Fahrenheit, and Fahrenheit to centigrade. So I'm spotting you the formulas that you can convert Celsius to any of those. If you have to do it any other way, you either have to have memorized the direct formula, or you have to use algebra to get you from, say, Kelvin to Celsius, and then turn around and use that answer to go from Celsius to Fahrenheit. So you need to practice on those. A couple of examples there. That's it for Chapter 1. Chapter 2, now we're going to talk about where this idea of atoms and molecules came from. And essentially the big peg point came in 1803 when a guy named Charles Dalton, he kind of figured this out here. Okay, sorry, I said Charles Dalton. I'm thinking Charles's law. John Dalton, the atomic theory. And so he came up with 5 rules for, if you will, putting atoms together. And guess what? They're true over 200 years later. The only change we had to make is we have to add the word chemical reaction, because some of these aren't true when you do a nuclear reaction. Of course, back in the 1800s, they had no clue, or even early 1900s, clue what an actual nuclear reaction was. Okay, let's see. Law of multiple proportions, there's an example of that. Basically, the punchline there is you can't use half of an atom. You're going to have a whole atom, and when you make something, and so you're going to have multiple proportions. Let's see. The little bit about the history, it goes into that. So as far as scientists goes, I have a 3-fold thing that gets me through most exam. Who is it? What was the name of their experiment? What's the punchline? That'll get you through most questions on a Gen Chem. If this is an analytical test, we would ask you details about this, but basically it'll be pretty much general. So J.J. Thomson did the cathode ray tube experiment, and in that he discovered the electron. And so you can look at that information and see kind of sort of how that happened. Okay, well, fine. He discovered the electron, but guess what? He only knew the charge to mass ratio. He didn't know the charge and he didn't know the mass. If you knew either one of those, you could calculate the other one from this equation. In enters Robert Millikan in the all-drop experiment. He discovered the mass of an electron. Good for you. So now that he discovered the mass of an electron, we could now back calculate the charge, and this brought things. This is a very, very clever experiment too, by the way. Remember, these were done back in the 1800s. Man, they didn't have much equipment. I mean, they have computers or nothing. They've got like a, this little squeeze bottle there is like one of the old perfume bottles. So anyway, these guys are pretty good. But they did have electricity. They did a whole lot with electricity and manual stuff. So the oil drop experiment, the book goes into that. Okay, so finally we knew we had positive and negative charges, and they thought they were distributed nilly-willy. And a guy named Ernst Rutherford did the gold foil experiment. Very cool experiment. Very, very cool. By the late 1800s, early 1900s, they had alpha particles. They had radioactivity, so it was really, really powerful. They started using that a lot, and he was able to discover that, no, it wasn't nilly-willy like this. It was all the positive charges kind of bound up in the center in a really, really tight knot, and these electrons are just kind of floating around on the outside, apparently nilly-willy. Okay, so there we go. So that's the protons and neutrons, and that's the protons and electrons and the nucleus. Only thing that was left was the neutron. They knew there was a neutral particle in there somewhere because of the mass. James Chadwick used radioactive bombardment of beryllium, and he discovered the neutron. This was about 30 years. They knew it was there, but it took a long time before somebody actually could discover it. So there's your summary of the 4 experiments and the people that did those. Now, what did they discover? Basically, what we're going to deal with is, and there's literally dozens and dozens of subatomic particles in chemistry. We're not interested in anything but electrons, protons, and neutrons. That will get it. Punchline here is that electron is much, 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 much lighter than a neutron or a proton. Has almost no mass, but its charge is every bit as big as a proton. Notice the magnitude of this is 1, and the magnitude of this is -1. In other words, the magnitude is just as big. An electron is just as strong on the negative side as a proton is on the positive charge, despite the fact that it's only about 1/2000th the size. That makes a big, big difference later. Okay, so then the book goes on to tell you about atomic mass, okay, which is protons, neutrons, atomic number, which is just the number of protons, and that determines who you are. And by that I mean if you have 6 protons, you're carbon. I don't care what this number is. If you're 6, you're carbon. All right, so there we go. There's different Carbons have different weights called isotopes. You got carbon that has 12 units, carbon that has 13, carbon that has 14. You got some, you can get them charged or not, but it doesn't matter. If you've got 6 protons, you're somewhere in the carbon family. There are 3 things that we're going to calculate typically, or really 4. Atomic number, atomic mass, the number of electrons, the number of neutrons, and the charge. Okay? So those are the 2 formulas that will help you calculate those. Notice Z, the atomic number, is common to both of those. And so that comes into play a whole lot. For example, I could give you A and N, and you could calculate Z, and then you could use that Z here if I gave you the charge also to calculate the number of electrons. So that's kind of a compound, a second level one where we combine these. The only thing that combines these 2, remember that, is atomic number. Okay, these are the type of questions you see. Who am I? If I tell you A is 12 and Z is 6, who are you? There we go. Right, a little bit of radioactive decay and this idea of isotopes. I just told you that's the same atomic number, different atomic mass. That goes on to get explained. Some more sample problems. And here's some that actually put charge into it. No big deal. Weighted average, that's how we do your average for this class actually. A weighted average, there's the 3 isotopes of magnesium, but we don't just take the straight average, because if you look at this, you'll see that about 79% in nature is this, and only about 10% and only about 0.1. So it gets weighted. So we're going to multiply this magnesium by a larger number than we are the other ones. So we're going to weight them according to their proportion in nature. And that's what we do with your exam, right? Your final exam is weighted 25%, and your midterm average is weighted, 45%, and then your lab is weighted 25%. So even though you have a number between 1 and 100 on each of those, they're weighted differently depending on their importance. And that's how you get the numbers on the periodic chart. How do they figure out how much something weighs? Well, that's pretty easy. Picture this as being a fan right here. Picture this as just being a fan to this blowing wind here. Okay, so if I have something very, very light like a ping pong ball, it'll just push it against this side and it won't come out the end. If it's yes, and if it's very heavy like a bowling ball or something, well, it'll go to the other side. So it's only when something is exactly the right size of that fan that it'll turn it just exactly and you can see it. So as I make the fan go faster and faster, I can tell whether something is heavier or lighter. And that's the main idea. Instead of a fan, we've got a magnet. Instead of weight of a ping pong ball, we've got the charge on an atom. So if I got a negative charge particle and it hits a positive charge, a negative charge of the magnet, it's going to bend away. And its size is going to determine how much it bends. From that, I can push something through that, and I can separate them based on when they come out. That is the basics behind mass spectroscopy. Chemical formulas, there's a bunch of types of formulas here, but we like to use the stick diagrams a lot. In this class, we will not use these space field models much. We'll use the stick models, the structural formulas a whole lot, and we'll just use the molecular formulas even more. There's another comparison of atoms and molecules. We've already been over that, said you need to know that. Let's see. Empirical versus molecular. Okay, it's some memory stuff. There's 7 diatomics, yes? Okay, so you need to know where those are on the periodic chart. The memory device, I was told by students, have no fear of ice cold beer. All right, so there we go. So you can remember those. There's 2 polyatomics. Phosphorus always lives as 4 together, and S lives as 8. And what we mean by diatomic is if you have hydrogen and you react it, you don't have just one H atom. They live in pairs. All of these naturally live in pairs. You can't find one without the other. They're handcuffed together. These are the little, I guess little commie things there, because these always live in groups of 4, and these always live in a commune of 8. You can't find just one sulfur unless you do some reaction. You're going to have 8 of them together. Okay, they live as a group of 8. If you take your molecular tweezers and pull one of those out, it's going to pull all 8 of them up. Empirical versus molecular formula, look over those, get the definition of those. There will be some problems where you separate those. Isomers, okay. That's where you have exactly the same formula. They're just put together different in shape. So if you see both of these, acetic acid and methylformate, how about that? They've each got a CH3 group. They each have an H. They each have a CO2 group. And yet they're very, very different chemically. They are isomers of each other. They have exactly the same formula. They just snapped them together differently. Okay. No big deal. Said you need to know the periodic chart. So for sure the stair step that separates what? Non-metals from metals. Make sure that you remember hydrogen is a non-metal. There's names for each of those four groups in particular. I would know that. There's a special name for these two rows or periods, and I would know those. The key thing you want to know from periodic chart is things above and below. And you'll learn exactly why later when we take quantum mechanics. But things above and below, that is, in the same group, typically share common properties. Oops. You need to know those two, and you need to know those two, and you need to know those two. There we go. The names of them. Elements versus compound versus, there we go. Again on that. I hit it like 3 times. It's like, please learn that. Okay, how to classify something. Again, that's the big thing, standard fare. Is it a molecule? Is it a compound? Is it an atom? Is it an element? Same thing. So, and by the way, anything that has a charge, even if it looks like an atom, Ca is calcium. Ca2 plus is not calcium. It's calcium ion. If it's got a charge, it's technically no longer an atom or molecule. It is an ion. So an atom or a molecule that's charged is just no longer an atom or molecule. Officially, it's an ion. Okay. Little nuance. Molecular versus ionic compounds. Here's what you want to know. Molecular compounds are typically made from things on the same side. They're both nonmetals. Ionic compounds are usually, if you look at that little diagonal there, it's usually a metal and a nonmetal. Most ionic compounds have one piece of it's a metal, one piece of it's a nonmetal. Most of your molecular compounds, both components are going to be nonmetals. Okay, classes of, there we go. So you've got different classes of ions. Actually drew it out on a chart for you. Nomenclature, there's some videos on that you're going to need to know. Lots of rules on that. So go over those videos in detail. Right, and there's some practice problems. The memory things, this is something else that you're told to memorize. You need to know that these 6, which we call the 6-pack, these are type 1 compounds. Type 1 metals. And these first 2, the alkaline metals and alkaline earth, they are type 1. All the other metals you can assume are a type 2, unless told other. No, that's not true. Some of them are type 2 and some of them are type 1. But to keep it simple, you owe me the fact that these 6 and those 2 rows are type 1, and you're allowed on an exam to assume if they're not type 1, they are type 2, unless told otherwise. So that keeps your memory down. But make sure what's in green, you got that memorized. Okay, there's some more examples. 3 types of compounds remind you: metal and non-metal where the metal's type 1, metal and non-metal where the metal's type 2, and 2 non-metals. And each of those has a different nuance to naming them. There's some 6 or 7 acids you're supposed to memorize. Here's 5 of them. Here's 1, 2, 3, 4, 5 of them. Phosphoric, sulfuric, nitric, carbonic, and acetic. I forget what the other 2 are. We'll see in a minute. Okay, so know how to do the families. Ic and us acids and 8 and 8 anions. That's very important for nomenclature. Okay, so I think the other 2 are buried in that. Yeah, chloric was another one, and I'm maybe nitric. Okay, so memorize those. All this is on videos. Let's see, more on that. This is just the binary acids. Okay, those are pretty straightforward. Some things have common names. H2O is not dihydrogen monoxide. It would be, but the powers that be just decided, you know what, we're just going to leave H2O water and be done with it. And NH3 is not nitrogen trihydride. It should be, but it's not. Ammonia is another really common material that they said, you know what, NH3, yeah, let's just keep it with ammonia. And by the way, the difference between ammonia and ammonium, ammonia is the charged neutral atom, and ammonium is the ion made from that. Okay, some more of that. Some more practicing nomenclature. I made a grid to help you through. The way I work nomenclature is I name everything as a type 1. If it's a type 1, I stop. If it's not a type 1, I then look to see if it's a type 2. If it is, I add a Roman numeral. If it's not a type 2, I go to type 3. And if it is a type 3, I add a prefix. If it's not, I then look at some of those other quadrants. See? It's either a type 1 or a type 1 plus a Roman numeral or a type 1 plus a prefix. That'll get me by most of the time. Really neat little trick. Okay, so there's a bunch of examples of going name to formula, and there's some going formula to name. Practice going both ways. They feel very, 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 very different. Okay, in the last chapter, we get into the harder stuff. For the most part, stoichiometry. So let's see, we got to do two things so we can do calculations in the world. One, we have to scale it up. Why? Because Mother Nature lives in the microscopic. Mother Nature sees two atoms and two molecules, and one molecule goes to two molecules. We can't see molecules. We can only see large stuff like grams. So we have to take her 2 to 1 to 2 proportion, and we have to scale it up to some number of grams plus 128 plus some number of grams. That's what stoichiometry is. So we have to scale up, and to do that, we're going to use Avogadro's number, and we're going to count by weighing, and to do that, we're going to use the molar mass from the periodic chart. That's it. Avogadro's number in the periodic chart. That's what all of this is about. Okay, and there it is. Scale up. To go from 1 atom to 1 mole, you multiply it by Avogadro's number. That's easy. When you do that, you can just change the word atom to mole. That's all you need to do. So, in other words, Mother Nature says 2 molecules, 1 molecule, 2 molecules. I say 2 moles, 1 mole, and 2 moles. I just scaled it up by a set amount. Okay, by the way, the reason that works is if you take 1 atomic mass unit and you scale it by Avogadro's number, it becomes exactly 1 gram. And so what that means is anything that's on the periodic chart, you can just change it with the word, you can just change AMU to G, and you can change atom to mole, and the proportions are exactly the same. It's a beautiful thing. Okay, so there's that. So how do we scale it up, though? How do we know to go to 12 grams? How do I know 12 of these goes to 12 grams? Why isn't carbon 16 here or something? Well, that's what I get from the periodic chart. So I'm going to get this number from the periodic chart. Now I'm going to use Avogadro's number to just change atom to mole and AMU to gram. Okay, those are details. That's why you do what you do. If you don't understand that, just mechanically do it. Okay. Right, how big is a mole? Some of that stuff really, really big, just so you know. When we talk about a mole of chemical, which isn't very much, let me see, what's a good one? If you took a mole of human cells, just 1 mole of human cells, you could make 6 billion people, most of planet Earth. Yep. If you have 1 mole of sand, again, not very much chemical at all, but if you have 1 mole of sand, if you scaled an atom up to the grain of a sand, it'd cover the entire United States 2.4. So when we say we have that 1 mole of hydrogen weighs 2 grams, well, that can't be very much. Oh, yeah. If you scale that up, if you scaled up a mole of that, you could cover the entire United States 2.4 inches. So we're talking about huge numbers. This very problem is worked in one of the videos, so I'm not going to go over it. Stoichiometry is covered in detail in a number of videos. So go over those. The next general type is called what I call the chemical calculations or formula calculations. And when you work on these problems, you're going to see there's 3 times. You're going to take a molecular formula and you're going to go to weight percent. That's typically one type of question. Some questions will give you weight percent and you determine empirical formula. Okay, that's what I call a type B question. And then type C is where the data question gives you the empirical formula and you have to go all the way back to molecular formula. Okay, a really hard question is you can start out here and have to go all this way. So that's like an A-level question. You use percent to get empirical formula and then use that piece of data to get you the rest of the way. So don't overthink these empirical and molecular formula questions. Even though you can word it a million different ways, there's only 3 basic types. Oh, by the way, this up here is a one-way street. This is one way. You're not going to go backwards. Okay, you're going forward. This is a forward thing. Okay. Just to let you know, basically graphically, the difference between an empirical and molecular formula. Picture a chain. If you got something that's 5 chain lengths long, that's your molecule. Each individual link would be the empirical formula. Yes? So this thing could be 5 lengths long or 100 million lengths long. It doesn't matter. The molecular formula changed, but guess what never changes? An individual link. So that's why the empirical formula is important. It gives you the simplest formula for representing something. That's where that comes from. Boy, here's a busy example where I started out with H2O2 and then converted that to weight percents, and then I took the weight percents and converted it to the empirical formula, and I took the empirical formula and converted it back. So I went all the way around the bend with just H2O2, just to make the point of how each of these works. Okay, and there that messy work is graphically. Okay, so I typed it out too. And then so what I normally do is the housetop thing, and I kind of remember this little, I call them the housetop, so I remember this is molecular formula, and that is percent, and that's empirical formula. And I read a question, and I look at what it gives me, and this one gave me grams and asked me empirical formula, so I know I don't have far to go. So just like I map my stoichiometry problems, I map these as well. Okay, so there's some examples of those. Let's see what else. Molarity. Don't overthink molarity. It is just a term of concentration. So far you've really only had one type of concentration. What's the weight percent say? What's the weight percent of chlorine in that? Okay, well we could do another one here. There's more ways to measure concentration. Yes? Okay. So what chemists typically use is this thing called molarity. And instead of how many grams there is in a liter of solution, or which is how much weight it is, we look at how many moles there are. Okay, so molarity is quite simply the moles of solute over liters of solution. And you'll see moles is the holy grail. That's where chemists live, 1 mole. Chemical equations, calculations, everything. Chemists take almost everything back to moles. Or if you're dealing with milliliters, you can work with millimoles. Okay, it doesn't matter. But the deal you need to know is molarity is moles per liter. By the way, if you rearrange that and do a little math, you get moles is equal to m dot L. Right? Molarity times liters. So this is a cute memory device. See the MOL. If you treat that little dot like a O. MOL equal MOL. Okay, it's not that impressive, but it's if you get in a jam in the pressure of the test and you're given this and you're given that and it says how many moles, you can use this little quick formula and just get it really, really quick. Okay, let's see. There's some sample problems. Again, I do molarity problems from dimensional analysis. The units are moles of solute over liters of solution. So you can do them however you want. I do all of mine through dimensional analysis so that I don't use something with the wrong units. Okay, and so I'm going to go through and do any number of exams, any number here. By the way, this is one where I could map it. It said how many grams if I look at my stoichiometry grid. There's grams right there. I box what I'm looking for. And where did it start me out with so many milliliters? Well, I know from my grid I can use milliliters to get the liters. Liters I can get the moles from what? Using the formula for molarity, and then I can go from moles to grams using molar mass. So that's how we can do that. Concentrations, dilutions, this is very easy. You just use a simple formula, MV equal MV. The general formula is CV equals CV. Concentration times volume equal concentration times volume. This is a great thing mathematically. You can see why it works out. But what this means is, if I know the molarity of compound B, if I know the molarity of a sample and how many liters it is, if I change it to a different molarity, I can tell how much liquid I had to add or lose to do that. Okay, and so there's some examples right there. So for concentrated solutions, you don't even really need to use the molarity equal moles per liter. You can just plug and chug in. This is one time I do not use dimensional analysis. This is so simple. I just plug and chug straight into the algebraic. I don't always use dimensional analysis, and you don't have to. Matter of fact, should you use dimensional analysis or should you do solve problems algebraic? The answer is do whichever one you're best with and you're quick with and you're efficient and you don't make mistakes with. That's what you want to use. Okay, there's another example of an MV-MV. The units of concentration, we already talked about mass percent. You're familiar with mass percent. Right, okay, let's see. Know how to do simple things like take weight percent and convert that to grams. Again, I do everything dimensional analysis. Let's see. There are some esoteric things. I wouldn't worry a lot about this, but sometimes things are reported in volume percent. I got this many milliliters of this and this many milliliters of that. Sometimes you have the mass of something and the volume of something else. That happens all the time in household products. I've got this many grams of this mixed in this many, ounces of water. So these aren't real common. You don't see these much in science. You see those on the commercial side. Parts per million and parts per billion, you betcha. I would know how to do that. Those are really, you can just use conversion factors. What is a part per hundred? It means a part per hundred is, so if you have something that's 17 parts per hundred, that's like, you just change that to 17 100ths, and then you can work with that as a dimensional analysis thing. There's some sample problems on that, and that is what you have on exam 1. So I don't know if that helps, but hopefully this video will at least help you either recognize something, see them in a different light, or maybe you saw me highlight something that you had totally skipped. Regardless, that's a wrap.